So in this part of the lesson, we're going to look at equivalent circuits, and we're going to look at if there is a difference between certain circuits electrically. And so this top one here, we have a resistor followed by a voltage source, and then the resistance on that is 100 ohms, and the voltage source is 1 volt. And then the circuit right next to it, we have those two switch. So the voltage source comes at the top, and then the resistor is 100 ohms that comes after it. And we're going to look, does it matter if the arrangement of a voltage source and a resistor, if they're in series? And the answer is no. So we're going to look at why that is mathematically, and then also what the implications are. So for instance, if you need to drop some voltage down so that you don't fry out an LED or something, then do you put the resistor before it, after it, or it doesn't matter? So the truth is it doesn't really matter. We're going to look at that mathematically as well. So in the bottom here we have another one which has a current source, a 1 amp current source, and then two 100 ohm resistors. And those, it goes current source, then resistor on the outside. And we're going to see that this drawing is totally equivalent to the one right next to it, where you have a resistor and then the current source, then a resistor afterwards. These are both equivalent circuits as well. So in this case, we're going to look at Kirchhoff's current laws and Kirchhoff's voltage laws for this to be able to see that these two, at least at the test points, are equivalent circuits. What equivalent circuits are? And so if the current and voltage characteristics at the nodes are identical, then the circuits are considered equivalent electrically. And identifying equivalent circuits simplifies analysis. That's the whole reason we do it, is to make it go faster. And sometimes you can get some interesting knowledge out of the system too without having to solve a whole bunch of smaller subsystems. So if we look at this original circuit segment, the one in the middle in pink, we're going to see that coming out of it you have an I2, and then going into it you have an I1. And you have a test point, V1 and V2. And remember, those little circles indicate a test point. And so the rest of the circuit then is to the right. What we're going to see is that this translates exactly the same as an equivalent circuit. So if you look down below, you can simplify some things into these black boxes. So another way of calling this is like black box circuits, where it doesn't really matter what's going on in the rest of the circuit for a lot of purposes. What really matters is some of the information about the system and how that's behaving. So a very, very simple example of this is if we look at on the right, we have combining in series resistors, and you've had this in physics where you can combine resistors in series and add them up. So in A, we have this original circuit, which is a voltage source. We have current going through resistor 1, 2, 3, 4, and 5. And this is going to simplify down into an equivalent circuit down below. So all of those resistors can be simplified into one resistor for this purpose of simplifying the circuit to an equivalent circuit. So as you can see, that's a lot easier from a circuit perspective. In the top one, you have 5 different components or devices, and in the bottom, you have one equivalent device or component. And so instead of having 5 different equations, R1 IS, R2 IS, R3 IS, yada yada, you can simplify them all out into R equals I. So that's the current going through the equivalent resistance. So why is this important? So now we're going to do it as more of an academic exercise, but later on it gets important to look at these equivalent resistances, because if you have a whole nother, say a whole nother computer board or a whole nother circuit or whatnot, that circuit is going to have a couple input and output jumpers on it. And so that circuit's going to be inputting some data and doing something mathematically to it, and then outputting some data. And so this way of doing equivalent circuits helps to simplify that system, so that therefore you have a given resistance and you can look at, you don't have to concern yourself with what that smaller additional circuit is doing. You can just pull the information you need out electrically so that you can connect to it. So we're going to look at this a little bit more. So here we're going to look at resistors in series, and this is something that we've done in physics, but we want to make sure we refresh so we remember it. So equivalent resistance in series is the sum of the resistances. So again, we're trying to simplify circuits out. So in order to get a more simple circuit, we can create a total resistance or an equivalent resistance of all those smaller resistors. So when you're doing that with ones in series, we can add them together. So there's another interesting part of this that's I'm going to explain here called the voltage divider, which is actually very useful if you're trying to do a couple different things in circuits, specifically if you're using variable resistors like potentiometers and rheostats. So a voltage divider. Essentially, we're going to look at this little circuit diagram over on the left, and we have a VS voltage supply, and then we have resistor 1, resistor 2, and then we have a V2, two test points that come off. So the way I like to think of a voltage divider is what percentage of the voltage is going to go through resistor 1 versus resistor 2. And so there's an equation underneath that, V2 equals R2 over R1 plus R2 VS. So essentially that's saying what percentage of the resistance is R2 versus the total percentage, and it's going to break that up. And so that's how I look at it. Mathematically, you can look at it the same way. This equation you can derive as you go through, or you can use Kirchhoff's voltage law to get it. So it's not critical that that you memorize this equation, but if you ever need to know how to get voltage down to a very set level, a voltage divider is a really good way to do that. And essentially, it's looking at the relationship between resistor 2 to the sum of R1 and R2. So on the right, we have another little diagram, same kind of deal. We have a 10-volt battery supply. We have a 3-ohm resistor, and then underneath that, a 2-ohm resistor. And essentially, it's saying what percentage of the power is going to go. What percentage of the voltage is going to go through come out and be dropped over the 3-ohm resistor versus dropped over the 2-ohm resistor. And so if you look at this equivalent circuit, that 3-ohm resistor is kind of like a 6-volt battery in the opposite direction, because it's dropping the voltage from 10 volts minus 6 to 4, which is left in the bottom, and that last resistor is dropping it down the final 4 volts, so it's like a 4-volt battery going in the opposite direction. So if you have a 10-volt battery and then a 6 plus a 4, which is a 10-volt battery, going in the opposite directions, they're going to cancel each other out. And so that's mathematically how we look at it. So a voltage divider is equivalent to subdividing a battery into two separate batteries. Again, useful for when you're trying to get a very precise voltage and you have a larger voltage as the source. So another way of simplifying resistors or simplifying circuits or creating equivalent circuits is the resistors in parallel. Again, this is another review from physics, but what we have is when we have a bunch of, if we look at the top left in picture A, this original circuit, we have a voltage source, and then resistor 1, resistor 2, and resistor 3. So what we can do if we're trying to find a simpler circuit from point 1 to 2, so again, we just want to know what those 2 points are. We don't want to know all the details that are happening in between them. Then we're going to simplify the circuit down to the lower circuit, which says we have an equivalent resistance, R equiv. And we can find R equiv by the sum of 1 over the different R's, so 1 over R1, plus 1 over R2, plus 1 over R3, and then take the inverse of that. And that's going to give us our R equiv. And so, again, this is useful because then you have the equivalent resistance of that, which can help you much easier solve IS coming out. So, furthermore, it can also let you find the individual currents going through, and if you're looking at individual currents going through, you get something here called a current divider. So we just looked at voltage dividers, but current dividers will take one incoming current and break it apart into smaller currents going down through the different resistors. So again, this is another equation that you don't have to memorize the equation for current dividers because you can always solve it by using Kirchhoff's current laws. However, it's a nice way that if you need a very set amount of current going through a resistor or some resistive package, that this is a way that you can break that that current down into more smaller controllable currents. So again, it functions the same as a voltage divider. It's kind of, the way I think of it, almost like a percentage of what percentage of IS is going down I1 and what percentage of IS is going down I2. So there's a lot in this one. We're going to do some more with resistors in parallel and adding them up, make sure that's clear. But sometimes this is a really great way to simplify a circuit, especially if the circuit or the problem is asking for something that doesn't involve all of these I1, I2, I3. So if we go back to picture A up in the top left, let's just say it says, here's the value of R1, R2, R3, and here's the value of the voltage, find IS. We don't need to find I1, I2, I3. That's just a waste of time. So we can create the equivalent resistance, solve V equals IR, and then solve for that IS, and then we're done. It keeps it nice and easy and straightforward, so it saves a lot of time. So in blue here, we have essentially the official definition of resistors in parallel and how to add them. But if you look at the very, very bottom left, R equiv equals 1 over R1 plus 1 over R2 plus 1 over R3, however many resistors in parallel you have, and then take the inverse of that, that's going to give you your equivalent resistance.